So this video is all about forces and the fact that they're going to generate the push and the pull behind everything that happens, right? They're the things that are going to drive all the motion that we've been dealing with so far for the entire first semester. So when we talk about those forces, okay, first thing we want to know is, what is a force? Well, force is a push or a pull, right? Push or pull in one direction or another. Okay, so it's going to have two things to it. It's going to be a vector quantity because it has both direction and it has magnitude. So it has an amount and it also is going to go in a certain direction. Okay, and one thing we're going to deal with in a little bit is understanding that the sum of all those forces that are going to act on a single object result in what's called the net force. Okay, net just meaning kind of the end result. What is the sum of everything that's acting on it, and what's the one thing that would replace all the forces? Okay. So how is force measured? Well, force is measured in newtons in the metric system, in pounds and English units. We're only going to focus on newtons, so don't worry about pounds, but there is a conversion factor between those two. But 1 newton, okay, is also written as 1 kilogram meter per second squared, which means that 1 newton of force is the force required to accelerate a 1 kilogram object at 1 meter per second squared. So if you put a box on a table and you pulled on it, and that box was 1 kilogram, and there was no friction on this table, and you pulled on it with 1 newton worth of force, okay, that box would accelerate at 1 meter per second squared to the right. So that's what forces are doing. Forces are things that are going to cause or attempt to cause a change in the movement of an object. They're going to attempt to cause an acceleration. They're going to attempt to cause things to start to move, maybe change direction, get faster, get slower. That's what forces are going to do. Okay? So I'm going to talk about different types of forces. So here, talk about tension forces. So in this picture right here, we've got tension forces in the strings, right? Okay, they're resisting a stretch. They are holding that person up in the air. Okay, they're resisting the pull down from gravity on that person. There's also lots of tension in all the muscles here, right? Those muscles are resisting stretching, resisting collapsing and letting that person fall to the ground. Okay, there's lots of different tension forces acting here. Even the bars that are holding up everything, supporting the rings, okay, on the sides, okay, they have tension in them because they're trying to be pushed downwards. So they're resisting some kind of motion. They're resisting a stretch or compression, and that is a tension force. Now, second force I'm talking about is weight. Weight is the force due to gravity. Okay, gravity comes from objects having mass. So when an object has mass, it pulls on things. Things are attracted to it. Okay, and our weight is the force due to the gravitational field of Earth. So you get on a scale, what you're really measuring is your weight. So this is the weight of this person right here. If they got on that scale, that's the amount of force they are pushing down on the springs that are inside the scale with. So that is the weight of the person. Next force is friction. Friction is going to be the interaction between two surfaces resisting motion. So in the case of this giant slip and slide, they've reduced friction by putting a bunch of water on top. But say if you put sand on top of it, okay, you're going to slow the friction down. Okay, if you made this like a grass hill, just pure grass, you're going to increase the amount of friction. Okay? And that happens because the two surfaces are kind of interacting with one another, and as something tries or is moving in one direction, the interaction between those two forces, between those two surfaces, is going to resist that motion. Okay? So friction can make it hard for things to start. It can also make things slow down as they move along, or making you apply more force to keep it moving. Fourth force is called air resistance. Okay, air resistance arises from the movement against air molecules of an object, right? And that force is going to be opposite of the direction of motion. So as things move, they run into air molecules, they bump into them, okay? And so in this case, you have the people falling down. So gravity is pulling them down this way, so that's their weight. Okay? And the air resistance is the resistance of those air molecules running into these parachutes, right? And when they do that, they're going to push that parachute up. So the person's pulling the parachute down, air is pushing the parachute back up. So that air resistance force, again, is in the opposite direction of motion. Okay. Another type of force that we're going to talk about, not really generate a type of force that's generated, okay, but it's a force that exists that's called the normal force, or also what's also known as the support force. So the normal force, N, acts perpendicular to a surface. So basically, it supports a portion of the weight that is also acting perpendicular to that surface. So here we've got an apple sitting on a table, right? The weight is pulling down on that apple, okay? Gravity is pulling down on that apple, and the table is pushing back up on that apple. And that is going to be our normal force. And let's try a different color because that's not showing up. Let's try green. That's not dark enough green. Let's go dark blue so you can actually see it. So we go here, and that normal force N is acting in that direction. So if this was a 4 Newton apple, the amount of normal force here would also be equal to 4 newtons. So it's the amount of force that's acting to support that object against the gravitational pull. So on a flat surface, it's pretty easy. Okay, if the thing's not falling through the flat surface, that normal force and the weight of the object will be the same. However, if we go here, now we have a person going down a hill, right? When we think about this, we know gravity is working straight down, the weight's going straight down, but we said the normal force acts perpendicular to the hill. Well, perpendicular in this case is this direction. So our normal force is actually going that way. It's kind of weird, right? Well, here's what's happening there, okay? So this weight, and you think about this, when you put something on a hill, okay, things don't want to just stay there, right? They want to go, so I'm going to draw that, they want to go down a hill, right? Okay. But gravity is acting straight down. So how is this possible? You know, we know gravity is causing it, but how is it possible, since gravity goes straight down, that that thing wants to go down the hill? Well, here's what really happens with the gravitational force. Okay? When that gravitational force is here, it's actually have two components. Just like we did with velocity, we have that weight force being broken down into two different axes that do two different things. So the first one, we'll talk more about this in a later unit, we'll do more of the math, but part of what gravity is doing is working this way. It's pushing the person into the hill, right? Making sure they don't go flying off the hill, they're going into that hill. So gravity's driving them into the hill. That's a portion of the weight, okay? The other portion of the weight, and this makes sense because when we put things on a hill, it goes down there, it tries to go down the hill, is going this way. We'll call that F down. So we have two parts to the weight. One is F down and one is F in. And what you might notice, might start to see, is that F in and the normal force are going to cancel each other out. Which is why when we put this person on the hill, that's the force that's going to cause them to move. So the portion of the gravitational force that's going down that hill, going parallel to that surface, is what's going to cause the object to go down the hill. The normal force and the portion of the weight going into the hill aren't going to do anything to the person. They're just going to keep them on the hill. Okay? So I said we'll mathematically break that down a little bit more later, but hopefully you can see those two components and understand that process. Okay. Now, net force. We talked about this a little bit earlier. Net force, this is going to be what drives our motion. What it is, it's this net force is the sum of all the forces acting on an object. Key is that it's an object. It is one object. It is not multiple objects. Okay? We get it by adding all the forces together, and that's going to give us a resultant. And when that happens, the object's going to accelerates in the direction of the net force. Okay? So for instance, here we got this person pushing a boat through the river. Okay? So there is resistance on the boat from the water, and since the boat's trying to go to the left, the resistance from the water is going to go this way. So here we've got some resistance. We've also have an applied force here from this big pole, okay? And the thing that's kind of funky is where it's actually being applied is at this guy's feet. So we've got an applied force this way. Okay? There might be some wind coming off here. Okay, maybe there's some wind over here. Okay, but the sum of all three of those forces together will dictate which direction this boat actually travels. Okay? We'll break into the vectors a little bit more later in mathematically deriving some of that, but understanding that adding all three of those together is what's going to give us our result. So if you have one force this way, a wind force going this way, and a smaller force going this way, well, this one here, maybe it's 10, this is 4, maybe this is like 2. Okay? What we're going to end up with is a net of 6 going this way, 2 going that way, which is going to result in, if we simplify it one more time, a boat that's kind of going in that direction, right? Kind of in between the 6 and the 2, kind of like this. It's going to go right there. Okay? We'll get into more of that later when we get into vectors and adding vectors with the next unit, but just understand that that net force is what's going to drive the acceleration. It's going to drive the motion of the object. Okay. So now we have a certain condition that called equilibrium. This is when the net force is 0 newtons. So in equilibrium, the object's motion doesn't change. There is no net force, so there is no acceleration. There's no change in the motion. So we're going to have two different types of equilibrium we're going to cover. One is called static, one is called dynamic. And these are two examples of those two situations right here. We'll break them down a little bit further. So here we've got static equilibrium, okay? This is when the object is not moving and the net force is 0 newtons. So we've got a sleeping puppy, right? So it's got its weight going down, it's got the normal force going up, no other forces acting on it. Object stationary, puppy's asleep, net force of 0, no acceleration. Your Jenga tower, gravity's pulling it down, the table is pushing back up, and as long as you're winning and it's not tipping and tipping over, hey, we've got a net force of 0, it's in static equilibrium. Statue of Liberty, same idea. Birthday cake, same idea. They're not moving, they're not going anywhere. There's no net force acting on them. Okay? That is static equilibrium. Dynamics a little bit different, but still there's no acceleration. The key is with no acceleration, that means we're moving at a constant speed and constant direction. We are not changing our speed and we are not changing our direction. The net force on the object is still 0, but the object is moving. So this person falling, say they're falling straight down towards Earth. They've got their parachute open, right? So they have their weight that's pulling them down, but the parachute is pulling them back up from the air resistance. And at some point, that weight and R, when W equals R, there's no acceleration. There's no change in speed. There's no change in direction. So this person falling is falling at a constant rate. That means that they are now in dynamic equilibrium. Okay? They're still moving. They're still falling towards the Earth. They just haven't changed their speed anymore. They're just not changing speed anymore. That is dynamic equilibrium. Okay. But what about when F net is not 0 newtons? Well, this is when the object will accelerate in the direction of the net force. So say this ostrich decides to go and start pulling on the little crate back here, right? The little wagon back there. Well, it's going to pull in this direction. It's going to exert an applied force that way. Okay? There's going to be some friction that's acting to the left, right? And we have our weight and we have our normal force. They're going to cancel each other out. But if FA is greater than F sub F, so let's say, let's draw it over here. So we have F sub F and we have FA. Oh, sorry, FA and F sub F. If the applied force is greater than the frictional force, well, F net's going to be in this direction. And that's going to cause the cart to gain speed and accelerate to the right. Okay? So if the applied force is greater than the frictional force, and we're trying to pull something along, it's going to start accelerating in that direction, right? Now, what about if the object is already moving, right? Say this train is moving to the right, and it's moving at a constant speed, okay? Or if it's trying to accelerate that way, right? Maybe it's got an applied force of this much right there, right? The train's applying that much force to the right, but Superman is able to apply an even greater force in this direction, okay? So we'll call this applied 1 and applied 2. Okay? Well, Superman's applied force is greater than the applied force of the train, so now my F net is going to be this way, and my acceleration, A, is to the left. Here's the thing though, even though the acceleration is to the left, it doesn't mean the train is going to turn around and go that way. The train has a velocity in this direction. If A is in this direction, A is velocity to the right, acceleration is to the left, what's going to happen? Well, it's going to slow down. That's what's going to happen. Okay. So if the net force is in the opposite direction of the motion, that object is first going to slow down until it comes to a stop, and then it'll turn around and speed up and go in the opposite direction. So hopefully some of this clears up some questions that you had, if you had any questions with forces in equilibrium, okay, and kind of gives you some clarity in terms of what we're talking about with net force and the different types of forces acting on objects.